Hi everyone, and welcome back to Chemistry with Kat. In today's video, we are going to be learning how to draw Lewis structures. Lewis structures can get very complicated, but in this video, I'm going to teach you the basics and some of my own foolproof rules that will prevent mistakes. Lewis structures are basically very simplified Bohr-Rutherford diagrams, which we already learned how to do. If you missed that video, I will link it here. The advantage of Lewis structures is that it's simplified. They're quick to draw. We can draw full molecules in Lewis structure form. They give us a lot of information about molecules and atoms with not so much work. Let's do it. Remember guys that I post new videos every day at 9 a.m. Please subscribe to my channel and turn on your notifications so that you're the first one to know about them. Lewis structures are called Lewis structures because the American chemist G.N. Lewis is the one who came up with them. Lewis structures show us three things. First, they show us the covalent bonds in a molecule. Second, they show us the electrons. And third, they show us the charges that are on an atom. And subsequently, they can show us the charge that's on a molecule. This is called formal charge, and we're going to cover it today, but we're going to go into greater depth in it tomorrow. The one thing that Lewis structures do not show us is molecular shape. Because of this, we can just draw our bonds at 90-degree angles or 180-degree angles, and we don't have to worry about it. It doesn't matter what level of chemistry you're in, whether you're in high school or second-year university, or heck, even doing your PhD, a Lewis structure will never show you molecular shape. We are definitely going to cover molecular shape on my channel, but just know that whenever you're drawing a Lewis structure, you don't need to show it. There are three foolproof steps to drawing a Lewis structure. First thing you're going to do is count up the electrons that belong in each atom, and then take into account the charge that's on the atom. For example, if a molecule has a 2- charge, you know that it's going to have 2 extra electrons on it. If it has 2+, that means that the molecule as a whole is missing 2 electrons. So step 1 is find how many electrons are going to be in the structure. Step 2 is drawing the skeleton of the molecule. And with this comes a little bit of a tricky part, and that's determining what is the central atom. There are a few rules that can help you find this, but sometimes you just have to know. One trick is finding the element that has the highest valence electrons. For example, sodium only has 1 valence electron, so you know that that's probably not going to be your central atom. Whereas nitrogen has 5 valence electrons, so that's probably going to be your central atom binding to other things. Another trick is going for the atom with the lowest electronegativity. And if you need a review on electronegativity, I'll link that video here. The reason for this is that bigger atoms have a lower electronegativity. So when you have a big atom, that usually means there's more electrons, so that will end up being your central atom. And lastly, anytime you are dealing with organic chemistry, your central atom is going to be carbon. So that is a pretty easy rule to live by. Once you have your skeleton drawn, you're going to start counting up the bonds. Count each bond as having 2 electrons. Then compare that number to how many electrons are supposed to be in your structure. Once you realize how many lone electrons you have to put, you can start assigning them. Any leftover electrons go on the central atom. Once the central atom is full, we can then start putting the extra electrons onto the most electronegative atom. This makes sense because the most electronegative atom is going to be attracting those electrons. Let's put those rules into action with a very simple molecule, hydrochloric acid, HCl. So here is HCl. The first step is counting up the electrons. Hydrogen is supposed to have 1 electron in its valence shell. And in the valence shell of chlorine, there's supposed to be 7 electrons because it's a halogen. There's no charge on the molecule, so I can just add these up, and that equals 8 electrons in total. So now I'll draw the skeleton of my molecule, step 2. Because there's only 2, I just have to draw H bonded to Cl. Even though it's linear, chlorine is technically my central atom because it has the highest valence. Now I start counting up my electrons. I count up the bonds first, and this bond has 2 electrons, but I have to get to 8 electrons. 8 minus 2 is 6, which means I have 6 electrons that are non-bonding, 6 electrons that aren't part of this bond. So I will start drawing them on the central atom. 1, 2, 3, 4, 5, 6. Luckily, I was able to fit them all onto the central atom. And now chlorine has 6 non-bonding electrons, and then they are sharing these electrons in a covalent bond. So that's 8 for chlorine. And then hydrogen is sharing these 2 electrons, and that's 2 for hydrogen. They both have a full octet, and they're happy. When I'm trying to count for formal charge, I count the bond as just 1 electron now. So I go 1, 2, 3, 4, 5, 6, 7. Chlorine is supposed to have 7, so I know that there's no charge. And then hydrogen has 1. So I know that there's no charge on either of these atoms, and there's no formal charge on the molecule. For my next example, I'm going to do carbon dioxide, CO2. So carbon has a valence of 4. Oxygen has a valence of 6, but there's 2 atoms. So I go 2 times 6. That equals 12 plus 4, which is 16. I'll draw the skeleton. Carbon bonded to 2 oxygens. And altogether here, I have 2 4 electrons in the bonds. So 16 minus 4 is 12. So I have to add 12 electrons. So I'll put 6 on the oxygen because it's the most electronegative, and 6 on the oxygen. Now I'll make sure I have 16 electrons, just in case I made a mistake. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have 16 electrons. Now I'll look at each atom separately and see how many electrons they have and if they might have a formal charge. Let's start with carbon. Carbon has 1 electron in this bond and 1 electron in this bond. So it only has 2 electrons. It's supposed to have 4. So that gives it a charge of +2. Now, the oxygens have 1, 2, 3, 4, 5, 6, and then 7 from this bond, when it's only supposed to have 6. So that makes it a -1 and a -1. Now, this structure is actually neutral because it has 2 plus, -1, -1 makes 0. The problem with this structure is that carbon does not have a full octet. If you count the shared electrons, it only has 4 electrons being shared with it when it's supposed to have 8 being shared. So what we'll do is we'll take some of the electrons from here and put them into a bond, and same with here. So our new structure will be carbon double bonded to oxygen, double bonded to oxygen. So now let's count up the electrons in the bonds. 2, 4, 6, 8. So 16 minus 8 is 8. So I have 8 non-bonding electrons. Carbon has the full octet now, so I'm not going to add it to carbon. But I'll add it to oxygen, also because it's the most electronegative. 4 on each oxygen. Now let's make sure we have 16 electrons. 1, 2, 3, 4, 6, 8, 10, 12, 13, 14, 15, 16. Perfect. Now we'll look at each atom individually. The carbon has 1, 2, 3, 4, so no formal charge. And oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Perfect. Now if we look at the octet of each one, oxygen is sharing 2 electrons from each of these bonds, so that's 4, 5, 6, 7, 8. Oxygen again has 8, And this middle carbon is sharing all 4 of these bonds, so it has 8 electrons. So here we have a neutral and correct Lewis structure. My next example is carbon monoxide, CO. Carbon has a valence shell of 4 electrons, and oxygen has 6. So altogether, we have 10 electrons. Let's draw the skeleton. C bonded to O. This has 2 electrons bonding, so 10 minus 2 is 8. I'll draw 6 on the oxygen. It's the most electronegative. And I'll draw 2 on the carbon. Now let's make sure we have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're good. Now let's look at each atom separately. Oxygen has 1, 2, 3, 4, 5, 6, 7 when it's supposed to have 6, so it has minus 1. And carbon has 1, 2, 3 when it's supposed to have 4, so it's plus 1. Now carbon doesn't have a full octet here. It only has the 2 electrons from this bond plus 2 more, and that's 4, and it's supposed to have 8. So let's put 2 of these electrons over here. Now our new structure will be C double bond O. Now I have 2 bonds, so 4 electrons in the bonds. 10 minus 4 is 6. So oxygen already has 4 electrons, so I'm only going to draw 4 on the oxygen, and then I'll draw 2 on the carbon. Let's make sure I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm good. But let's look at each individual atom. 1, 2, 3, 4, 5, 6. Beautiful. 1, 2, 3, 4. Beautiful. They're both neutral. But let's make sure they each have an octet. We have 2, 4, 5, 6, 7, 8. Oxygen has a full octet. Carbon has 2, 4, 6. Still not a full octet. So let's draw one more time. C triple bond to O. So now we've taken the electrons from the oxygen and added a triple bond here. So we have 3 bonds, that's 6 electrons that are bonding. 10 minus 6 is 4. So I have 4 electrons left over. Oxygen has 6, so I'll put 2 over here. And hydrogen has 6, so I'll put 2 over here. Let's make sure I got 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm good there. Each atom separately has, oxygen has 1, 2, 3, 4, 5 when it's supposed to have 6. So oxygen is plus 1. Carbon has 1, 2, 3, 4, 5 when it's supposed to only have 4. So carbon is minus 1. Does each atom have the full octet? We have 6 being shared, 7, 8, 6 being shared, 7, 8. So they each have a full octet, but they both have a charge on it. Now, overall, these 2 charges cancel each other out, so the entire molecule is neutral, just like we have at the start with CO. It seems weird, but even though the atoms in this molecule are both charged, this is the correct Lewis structure for carbon monoxide. My trick question for today is ozone, O3. Oxygen has a valence shell of 6, and 3 times 6 is 18 electrons. So let's draw oxygen 3 times bonded. I have 2 bonds, so that's 4 electrons. 18 minus 4 is 14. So I still need 14 electrons here. I'll put 6, 3, 4, 5, 6. I'll put 6. So that's 12, and then I'll put 2 over here. So altogether, let's make sure I have 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'm good. Now I look at each atom individually. This oxygen has 1, 2, 3, 4, 5, 6, 7 when it's supposed to have 6, so -1. This oxygen has 1, 2, 3, 4 when it's supposed to have 6, so that's +2. And then we have 1, 2, 3, 4, 5, 6, 7, -1. This is a neutral structure, but let's check our octet rule. The oxygens on the ends both have 8. They have 6 non-bonding electrons and 2 coming from the bond. This oxygen has 2 coming from this bond, 2 coming from this bond, so there's 4, but 5, 6, so it's missing its full octet. This isn't right. Let's take a pair of electrons and add it to a bond. So we'll go oxygen, double bond, oxygen, to another oxygen. Now we have 3 bonds, which is 6 electrons. So 18 minus 6 is 12. So now I have to add 12. I'll add the 6 here again. Now to here, I'll add 4. And I'll add 2 here. Let's make sure I have 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Perfect. Each atom individually, we already know that an oxygen that has 6 plus this 7 is going to be -1. This one has 1, 2, 3, 4, 5. So that's +1 now. And then this oxygen has 1, 2, 3, 4, 5, 6. So it's actually normal. Now let's check our octet rule. This has 4, 5, 6, 7, 8. So that's good. This has 6, 7, 8. And this has 2, 3, 4, 5, 6, 7, 8. So the octet is actually set. But let's say for fun, you want to put these 2 electrons over here. Let's see what that would do. Oxygen, double bond to oxygen, double bond to oxygen. 18 minus 8 is 10. So I'll add 4 here, like I had before, 2 in the middle, and 4 over here. Let's double check that that's 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Perfect. Each atom individually, this has 2, 4, 5, 6, 5, 6, good. 2, 3, 4, 5, 6, neutral. 2, 3, 4, 5, 6. They all have 6 valence electrons and no charge. But let's check our octet rule. We have 4, 5, 6, 7, 8, so this one's good. We have 4 bonds, so that's 8, 9, 10. We can't do that. And this one has 4 coming from the bonds and then 5, 6, 7, 8. So this one, with all 3 oxygens having the full octet, is the correct Lewis structure. I made this the trick question because most students will see these charges and think, oh, I can do it like this, and make sure that there's no charge on each of the oxygens. But you cannot ignore the octet rule. Make sure in a molecule that every atom has a full octet of 8 electrons, or else it's not correct. The charge is fine as long as they balance themselves out, because O3 is neutral. If O3 wasn't neutral, we could have an imbalance of charge here. We're going to review that in my next video tomorrow. All right, guys, for homework today, I would like you to try to draw the Lewis structure for nitric acid, HNO3. I'm going to put the answer on my Instagram at ChemWithKat right when this video airs, so go over there to check the answer. I'll give you a few hints. Your central atom is not actually the one with the most valence, it's nitrogen, hint, hint. The second hint is that the hydrogen is not binding to the nitrogen directly. Good luck. If you enjoyed this video, please give me a thumbs up and subscribe to my channel for more lessons. I post every day at 9 a.m. and I want you guys to ace chemistry when it starts up in the fall. So let's do it. See you next time.